Hey y'all, welcome back to another 15-minute summary of a section from Rogawski's 4th edition calculus. In this video, we're going to be talking about section 2.6, which is all about the squeeze theorem and trig limits. Don't get too worried when we say trig limits. We're actually going to have some nice theorems that we just get to apply, two in particular, that if you just kind of force them to happen, bam, you got your answer. Let's dive in. Now I want to start the video trying out an example. So here we got the limit as x approaches 0, x squared times sine of 1 over x. Now normally with our kind of 2.4 mentality slash 2.3, we just try plugging in the number. But notice we get 0 times sine of infinity. So plugging it in really doesn't work. Okay, next step would be let's try to go ahead and do some algebra with this. I don't got any algebra. So we clearly need a different way of solving this. Now, what we can always do to get an intuition on the problem is go to a graph. All right, so here we have a graph of y equals x squared sine of 1 over x. Now, this is the function that's in question, and we were trying to figure out the limit as you approach x equals 0. So notice as I zoom further and further in towards 0, it's pretty clear where the function limits to. And in fact, if I click on it, oh, well, we get undefined, but you can kind of see that real close to it. Desmos doesn't even really give it the credit of a decimal. It just says 0. So clearly the limit is 0. Now, one thing that is going to be helpful to us is maybe what we can do is create some bounds on the function. Now, I'm going to propose two bounds right here, y equals x squared and y equals negative x squared. Things to notice about this. First off, x squared is bigger than the function always, and negative x squared is smaller than the function in question always. Even when we zoom further and further down, you can kind of see it almost sandwiches it. It almost squeezes it together. Well, if I did the limit as x squared, of x squared as x approaches 0, I'd get the answer 0. And if I get the limit of negative x squared as x approaches 0, I'd also get 0. Well, that's what the squeeze theorem is basically saying. If you have a function above you, x squared, and a function below you, negative x squared, who have the same limit, 0, turns out that since you were squeezed between that, you also have to be 0. So now from the graph, we notice that the answer to this has to be 0. Now how we can go about proving it is going to be by using an upper and lower bounds like you saw on the graph. So what can we do to go ahead and bound this function? Well, one thing that we want to notice is that sine takes in an angle, spits out a ratio, will always be bounded above by 1 and below by negative 1. So we can absolutely say that this is the case no matter what the x involved is. Nice property of sine and cosine, works for cosine as well. Well, maybe we can kind of build this function based on this inequality. So what if I multiply by x squared on both sides? Giving me negative x squared, I guess I should say all three things on both sides, is less than or equal to x squared times sine of 1 over x, which is also less than or equal to x squared. Now normally I'd have to be a little bit careful in doing this. I'd want to say something like the absolute value of x squared on these far sides to make sure that this is the most negative you can be and this is the most positive you can be. But since x squared is a non-negative function, we really don't have to be this overly careful. But notice that now that we've multiplied through by x squared, we're left with our original function. And what I'm claiming is that this guy is always less than or equal to this guy, which is always less than or equal to this guy. Well, if your functions follow this inequality, you should also have that your limits follow this inequality. So that the limit as x approaches 0, and you're usually best to go ahead and throw the absolute values on no matter what, is less than or equal to the limit as x approaches 0 of the function we care about, is less than or equal to the limit as x approaches 0 of the absolute value of x squared. This is absolutely true since our function values are always following that inequality. But notice that the limit as x approaches 0 of this guy, that's a perfectly plug-inable thing. If I just plug in 0 to it, I get an answer of 0. Similarly, on the far right-hand side, if I plug in 0, I get an answer of 0. If you had to be a number, like this guy is, between 0 and 0, it turns out that you have to be 0. It's the only number between it. So, based on this squeezing in from a lower and an upper function, we actually have that the limit as x approaches 0 of the thing we care about, which I'll shorthand as f of x, is 0, confirming our answer that we got graphing-wise. This is the squeeze theorem. Get a function that you have a question about, find something above it and something below it that have the same limit at the point that you care about, and then just go ahead and note that the thing in the middle is trapped. It's squeezed down to be between 0 and 0. It has to be 0. Let's now evaluate this limit using the squeeze theorem. So always worth noting, you can always try to plug it in, but notice we get this cosine of 1 over 0 thing, so we're going to need to try something else. The squeeze theorem works. So the very first thing I want us to notice is since we have a cosine, we can say that cosine is bounded by -1 as a lower bound and +1 as an upper bound. Now, where we get into a little bit of ambiguity is going to be this t squared minus 4. So one thing that we can also say about this, because notice that if you are less than 2 but like really, really close to 2, so for instance like 1.5, this term is actually going to be negative. So I can't just quite say this is less than or equal to negative t squared minus 4 and greater than or equal to positive t squared minus 4, because throwing this negative, depending on your t, might really screw some things up. So this is actually where we want to say something like this. T squared minus 4. Well, if I take an absolute value of it, I know that you are going to be less than or equal to it. So we definitely have that. Now for a lower bound, we got to be careful. Now what we can say is we can take the absolute value of it and throw a negative outside on it. Now why does this work? Well, if I have a t such that t squared minus 4 is negative, I can't just have parentheses right here because a negative times a negative will give me a positive. Positive cannot be less than or equal to a negative. So by throwing the absolute value bars on it and then a negative on the outside, I am making this side be a negative number. That has to be less than or equal to t squared minus 4. That's where we need the absolute value bars. Now if we combine this information, we can figure something out. In particular, we can figure out that negative t squared minus 4, the absolute value of, better be less than or equal to t squared minus 4 times cosine of 1 over t minus 2, which all better be less than or equal to the absolute value of t squared minus 4. The absolute values just ensure that our negatives and positives are playing nicely together and that we really have inequalities holding. Well, ultimately, if we take a limit on everything, we'll find that the limit as we approach 2 will give me 4 minus 4 will give me 0. So 0 is the limit as t approaches 2 of the negative absolute value of t squared minus 4. Now this is definitely less than or equal to the limit as t approaches 2 of the middle guy just by this inequality line. Which by the same inequality line has to be less than or equal to the limit as t approaches 2 of the absolute value of t squared minus 4. But then, by plugging in our number, we can see that this is also 0. What number is trapped between 0 and 0? Well, it has to be 0, squeezing this limit down to equal 0 by the squeeze theorem. Now here are two rules besides the squeeze theorem for the section that we will be using for most of the homework. And they both come from the squeeze theorem. Definitely give it a look in a textbook to see what the lower and upper bounds are for each of these guys. So first off, the limit as x approaches 0 of sine of k times x divided by k times x, where k is just a number that's not equal to 0, turns out that this limit is 1. Turns out that the limit as x approaches 0 of 1 minus cosine of k times x divided by k times x, well, that has to equal 0 so long as k is not equal to 0. Now I'm including this k because if I have a 2 right here, so long as I have a 2 down here, coupled with the x's of course, we have that these limits hold. It doesn't matter, I just have to have whatever's on the inside of cosine repeating itself on the bottom, where it's just kind of a simple multiplication like this. If we can force these situations, turns out we know what the limits are. And moreover, so one thing that might come up, if I have that these guys are even flipped, I know that my answer is still going to be 1. The reason for that is if I think about flipping this, I would probably have a flipped answer, and 1 divided by 1 is still 1. Now this doesn't hold that flipping property for this, so we really do need 1 minus cosine on top, because if I were to flip this, 1 divided by 0 ends up being infinite. To see what I mean, let's go ahead and try an example out. Here we have the limit of the sine of 3x divided by the sine of 7x as x approaches 0. If you were to plug in 0, you would get 0 over 0 indeterminate. But luckily, what we can try to do is force the situation in the previous frame of the video. We can try to get sine of 3x divided by 3x and 7x divided by sine of 7x. That's why I was talking about flipping them. Sometimes signs appear on the bottom, but so long as we kind of have that opposition from the rule, we're good to go. Now, one way I can force a situation is by creatively multiplying by 0. For instance, by 1. Multiplying by 0 blows everything up. If I multiply by 3x over 3x and by 7x over 7x, I can just kind of creatively rearrange this multiplication to give me what I'm looking for. For instance, if I just so happen to put this 3x beneath sine of 3x, it all of a sudden looks a lot like our rule. If I just so happen to put this 7x on top of this sine of 7x, that also looks like a rule, just kind of inverted. Now notice I've used the 3x and I've used the 7x, and I have an x on top and bottom which can cancel. So I'm left with the fraction 3 over 7 on the outside. Now if we were to take this limit, turns out we can just kind of take the limit of each individual thing. By our rule, this limit right here limits to 1. This function right here also limits to 1. And last but not least, this guy right here just stays 3/7, ultimately giving us an answer of 3 over 7. That's how we use these trig rules. As the last example, let's go ahead and try this guy out. Now the limit as h goes to 0 of 1 minus cosine of 2h divided by sine squared of 3h looks like we can go ahead and start to think about using our trig identities. So what I need to have a 2h on bottom and a couple 3h's on top. Let's see if we can get that. So, as I said, since we want a 2h on bottom, we can multiply by 2h divided by 2h. Now with sine squared of 3h, recall that sine squared is just sine of that angle times sine of that angle. So I'm going to want 2 copies of 3h on top. Meaning I have to multiply by 3h over 3h 2 different times. Doing some clever rearranging, what I'm going to do is copy a 2h beneath 1 minus cosine of 2h. Also, so I'm going to split this up and write sine of h, or sine of 3h on bottom of one fraction, and sine of 3h on the bottom of another fraction. Ultimately, I want a 3h and a 3h right here, which is why we multiplied by these guys. Now let's track what's left over. I used one 2h on bottom, and I used two 3h's on top. This leaves me with, a 2h on top, and 3h squared, 3h times 3h, so 3h squared, just with different parentheses on bottom. Now here's one issue that's coming up. Notice that although I get 0 for this limit by our rule, 1 and 1, that once the dust settles on the simplification, I'm going to have 2 over 9h. If I plug in 0 to that, I'm going to get infinity. Or does not exist, I should be more specific. But 0 times that thing is going to be an indeterminate form. So sometimes we're going to need some added oomph to our theorems. This is going to be where trig identities come into play. So luckily we have the trig identity for double angles that cosine of 2 times your angle is actually the same thing as 1 minus 2 of sine squared of that angle right there. So since we know this identity, we can actually go ahead and use this to go ahead and compute. So this is why we get trig, this is why this section is called trig substitutions as well, because ultimately you might have to do some of these rules that we learned in pre-cal. If I use that rule though, what I'll get is 1 minus 2 sine squared of h divided by sine squared of 3h. Now the top ends up simplifying out to just, well, 1 minus 1, those cancel, but then we'll get a negative 2, so we'll get positive 2 sine squared of h divided by sine squared of 3h. Now to take advantage of our rule, what we're going to ultimately want to have is an h on bottom for each copy of sine h, and a 3h on top for each copy of sine of 3h. Therefore, we're going to need to multiply by h over h twice, as well as by 3h over 3h twice. Now once I split these guys up, what I'm going to end up with is 2, I'll just write that big 2 on the outside, of sine of h, taking one of those, dividing by h. I have another sign on top, so I'm going to grab the other h from the bottom. So kind of use both of those. Similar fashion, I'm going to take this guy and put a 3h over top of it. And do that one more time. Oh, excuse me, we used them on top this time. Now what I'm left over with is an h squared on top, as well as a 9h squared on bottom, leaving me with the fraction 1 over 9 as the leftovers. Ultimately, if we take this limit then, we're guaranteed to have 2 times 1 times 1 times 1 times 1 times 1/9, which gives me a final answer of 2/9. So sometimes we have to use a trig substitution before we use our trig rule. Thanks for tuning in to this section 2.6 recap. I know it's a little bit over 15 minutes, so I apologize if it was. There's just so much to talk about with calculus. So big things, remember that the squeeze theorem helps you find the limit when you can't really do algebraic simplification by bounding it by an upper and a lower function. While we have some nice tools to figure out sine of x over x as you approach 0, and 1 minus cosine of x divided by x as you approach 0, which is all thanks to the squeeze theorem. Next time we're going to be talking about infinite limits, so be sure to go ahead and attempt your homework, and good luck.